Hi everyone. Let us solve this theorem. Let us discuss the proof of this theorem. Okay. Actually, it is looking so much lengthy, but don't worry. We'll solve one by one. Many sub-bits are there. Getting. So see, first of all, we have to prove it power series converges uniformly in this interval. After that, we have to prove if it's continuous, differentiable, integrable, and formula of Cn is equal to this one. Okay, don't worry. We'll solve it one by one. So first of all, I will write the given thing. What is the given thing? R is a radius of convergence of power series. Okay, let me write that thing. Okay, so this is a given thing. R is a radius of convergence. Okay, so R is a radius of convergence. That means this series is convergent. Okay, for each point of interval minus R to R. Yes, so summation Cn x raised to n is convergent for any x belongs to interval minus R to R. See, we have a one more data, which is 0 less than s less than R. Okay. See, s is strictly less than r. So that means we can find some point between s and r. So there is a strictly inequality. So that's why you can find one point between s and r. Okay, so see, x naught is less than r. That means obviously it lies in the interval minus r to r. See, but minus r comma r is a interval of convergence and x naught lies in the interval of convergence. So therefore that series convergent at x naught. So therefore summation Cn x naught raised to n, this is x naught raised to n is convergent. But you know that when any series is convergent, the necessary thing is the corresponding sequence should converge to 0. So it converges to 0, so yeah, I wrote the same. Therefore this sequence, the same thing we can write in another way, that sequence is converges to 0. So we can say it's a convergent sequence and converges to 0. But we know that every convergent sequence is bounded. So that's why we can say it's a bounded sequence. You remember the definition of bounded sequence? Yeah, bounded sequence means there exists m belongs to set of natural number and so and so. Not natural number, positive real number such that mod xn cn x naught raised to n less than or equal to n for every natural number, right? So yeah, this part we have done. See what we have to prove? We have to prove that this series converges uniformly on interval minus s to s. Okay, so for that purpose I will take any point from interval minus s to s and we will consider mod cn x raised to n. Okay, so you can take separate mod. I'm going to add just x naught also, x naught raised to n also. So we'll have this thing. You understood now what I have done? I have multiplied by x naught raised to n, I have divided by x naught raised to n. Okay, but see, equation 1 says this term is less than or equal to m. Okay, so we get this is less than or equal to m x upon x naught raised to n. But see, basically here x belongs to which interval? Minus s comma s. So therefore mod of x less than or equal to s, but our x naught is greater than s. On last page we have written our x naught is greater than s. So what can I write here? Here we can write this thing. So after that means mod x less than x naught. I will shift x naught on this side. So you'll have less than 1. You can write mod to x naught since it's positive. So if you write mod or doesn't write mod, it doesn't matter here. Getting? So see what I want to say. So therefore summation m mod x upon x naught raised to n is a geometric series. Okay. And what is its common ratio? Common ratio is mod x upon x naught. See, but we have already proved it is less than 1. So therefore it is less than 1. So therefore you know that if you have a geometric series with common ratio less than 1, so then obviously it is convergent series. So that's why I wrote this is convergent series. Okay, I will call it as equation number 2. Which one? Here. This is equation number 2. See, here we are saying mod cn x raised to n less than or equal to this one, but this is convergent series. Then we can apply Weierstrass M test. By Weierstrass M test we can say this is uniformly convergent series. So therefore by Weierstrass M test what can we write? Summation cn x raised to n is uniformly convergent on interval minus s to s. Since we had taken interval minus s on last page, I can show you here we had taken x from minus s to s. So that's why it is uniformly convergent on minus s to s. Okay. So this first part is done. Okay. So let us go further. So after that we have some given information. Okay. I can show you in a problem. What is a given thing? So yeah, we have proved it is uniformly converges on minus s to s. We have to prove that with given thing is, so that series converges to f. Okay, so I will write that thing. So this is a given part, that series converges uniformly to f. So same thing we can write as the series is nothing but f of x. Okay, I will call it as equation. I think equation, two equations we use. I will call it as equation number 3. Okay, so let us focus on the first subequation. What is the first subequation we have? We have to prove that f is continuous on interval minus r to r. Okay, so see clearly Cn x raised to n is continuous functions. It's a polynomial function, so that's why it is continuous on minus s to s. As well as we have, and that series converges uniformly to f. See each function fn of x is continuous and converges uniformly to f. So we have a result. So using that result, we can say f is also continuous on interval minus s to s. Okay, but see, this is true for each s. You remember the condition on s, that was 0 less than s less than r. So with the help of that, it is true for each s now, which is less than r. So therefore, if it's continuous on interval minus r to r, open interval. In this way, we completed the first part. Okay, let us go for the second. What is the second? If it's continuous on minus r to r is done. Let us go for, so for any x belongs to minus r to r, this is a result related to integration of function. Okay, so see, let us consider, let x belongs to open interval minus r to r. Then clearly we can write that Cn t raised to n is actually, last time we had taken Cn x raised to n, na? But this time I took Cn t raised to n, since x is already we have used, na? So Cn t raised to n is integrable. It's a polynomial, that's why it's an integrable function. Okay, that series, okay, converges uniformly to f. See, I wrote actually we have a series this one, but we are writing in terms of t, so it's converges uniformly to f on interval 0 comma s. Actually it is converges uniformly on interval minus s to s. So this is the smaller than this one, so obviously it is converges uniformly to on interval 0 comma s. Okay, so that's why what can we say? See, I will read it again. So this is integrable function and summation converges uniformly to f. So that's why f is also integrable. And one more thing we have, this result already we have proved, huh? And integration of f is nothing but, see, we can take summation outside, integration of c and t raised to n. This is one result already we have seen. Okay, so cn is a constant, will come outside, and integration of t raised to n. What is the integration of t raised to n? Yeah, obviously t raised to n plus 1 upon n plus 1. After that, we will put upper limit, lower limit. If you put upper limit, you will have x raised to n plus 1 upon n plus 1. If you put lower limit 0, you will have 0. So that's why we get, okay, this thing. Okay, so in this way we completed the second subequation also. See, this part is also done. Let us go for the third one. Okay, if it's differentiable. See, we have clearly Cn x raised to n is differentiable. See, it's a polynomial function, that's why it is differentiable on interval minus s to s, and this series converges uniformly to f on interval minus s to s. Nothing is new, many times so we have already written. And 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 summation n Cn x raised to n minus 1 converges uniformly in interval minus s to s. This is a new thing I am writing. Okay, so how could I write it? Actually, the series, see, have same radius of convergence. These two series have same radius of convergence, so that's why we could write this. Actually, this is a statement of one very big theorem we have already proved, that Cn x raised to n is differentiable, converges uniformly to f, and its derivative series is also uniformly convergent. Okay, so therefore what can we say? Therefore f is differentiable on interval minus s to s, and f dash of x is equal to this one. Okay, on interval minus s to s. So this is one theorem we have used here. Okay, so see, actually this is true for each s, okay, such that 0 less than s less than r. Therefore we can write the same things for interval minus r to r. In this way we completed third subequation also. So let us focus on the last. Now simply we have to prove Cn is equal to nth derivative of f at 0 upon n factorial. This is a last subequation. Okay, so I can write similarly f dash of x. I could write this now. So can you tell me what can we write about f double dash of x? Obviously you have to take one more derivative. N and Cn are constant. What is derivative of x raised to n minus 1? It's n minus 1 x raised to n minus 2. So therefore n minus 1 Cn x raised to n minus 2. I can take one more derivative. Then tell me what is your f triple dash of x? Yeah, please tell me. It is summation n minus 1 n minus 2 cn x raised to n minus 3. So can you tell me about mth derivative? Yeah, please try to say mth derivative. What will be your mth derivative? Yeah, see actually here I need to write 2, huh? Since 1 is not applicable, otherwise you will have a negative number 2. So see, yeah, summation. Yeah, please. Sorry, here we have to write 2, since if you put 1 otherwise you will have 0. If I put 2 here, you will get 0. So here it should start from 2, here it should start from 3. So for mth derivative, obviously n will start from m, since we are calculating mth derivative. Yeah, beginning will be same, n minus 1 n minus 2, and you have to go up to, yeah, when you have a third derivative you go up to 2 n minus 2, when you have a second derivative you go for up to n minus 1. So for nth derivative, yeah, n minus m plus 1. Okay, and cn x raised to n minus m. Okay, so if you expand this summation, what will you have? Expand, that means first we put m, after that we put m plus 1, and so on. I'm going to expand, huh? If we put n is equal to m, we get this one, m minus 1 m minus 2 up to m minus m will get cancelled, and we will have 1, and cm x raised to m minus m, which is 0, plus, now I will put m plus 1, m plus 1, m plus 1 minus 1, m minus 1 up to go up to 2, and cm plus 1 x raised to m plus 1 minus m will get cancelled, x plus, and so on. Okay, so now what will I do? I'm going to put x is equal to 0. So tell me what will you get if I put x is equal to 0? Left hand side, obviously, x raised to m 0. If I put x is equal to 0, but here already power 0, that means 1. So you will have the first term. Plus, if I put x is equal to 0, 0 into anything, 0. And all remaining terms you will have x. So if you put x 0, you will have 0, all terms 0. So that means, yeah, oh sorry, if I go to write cm here, huh? Cm. So see, so have you seen m minus 1, m minus 2, and so on, 3 into 2 into 1. So it's a factorial. So we get mth derivative of f at 0 is m factorial into cm. Remaining terms are 0. So obviously, what is our cm? Cm is mth derivative of f at 0. I am shifting m factorial on this side. So it is m factorial. So this is required cm. So see, same thing we have to prove. Just they have called for C0 and we have calculated for cm. That's it. Thank you.